Hello everyone. In this video, we are going to learn about the deadlock avoidance. Deadlock avoidance, it requires that the system has some additional information about how resources are to be requested. For each request, the system should consider the resources which are currently available, the resources which are currently allocated to each process, and future request and release of each process. So we need to decide whether the current request can be satisfied or it must wait to avoid the deadlock. The simplest and most useful model requires that each process declare the maximum number of resources of each type that it may need. The deadlock avoidance algorithm dynamically examines the resource allocation state to ensure that there can never be a circular wait condition. Resource allocation state is defined by the number of available and allocated resources, also the maximum demands of the processes. Some of the basic facts. If a system is in safe state, there will not be any deadlock. If the system is in unsafe state, there is a possibility of deadlock. Avoidance, it ensures that the system will never enter an unsafe state. In this picture, we could see this represents the safe state, this is unsafe, and this is the deadlock state. So if the system is in this unsafe state, there is a possibility of deadlock. If we are avoiding the deadlock, we can ensure that the system will never enter this unsafe state. Also, not all unsafe states are deadlocks. This unsafe state may lead to deadlock. So behavior of processes can control the unsafe states. Safe state means the operating system can avoid unsafe and deadlock states. Resource allocation graph scheme. Consider this resource allocation graph. Here, there is a climb edge. Pi makes a request to Rj. You could see it's a dashed line. This edge is a dashed edge. So P1 to R2 there is a climb edge. P2 to R2 there is a climb edge. This climb edge implies that the process P may request the resource R at some time in future, and at present it's represented by a dashed line. This climb edge will get converted to a request edge when a process is making a request to the resource. That request edge will be converted to an assignment edge when the resource is allocated to the process. When a resource is released by a process, the assignment edge reconverts to a climb edge. That is, the idea is, this is a climb edge at present. In case the process is making a request to the resource, this climb edge will convert to a request edge like this. This request edge will convert to an assignment edge like this when the resource is allocated to the process. After using that particular resource, when P2 releases the resource R2, this assignment edge again it reconverts to a climb edge. This is how it works. Resources can be climbed using a priori in the system. That is, before the process starts executing, all its climb edges must appear in the resource allocation graph. In this resource allocation graph, Pi is requesting Rj, for example, and it is granted only if converting that request edge Pi to Rj to an assignment edge Rj to Pi does not result in the formation of a cycle in resource allocation graph. So assume the Pi is making a request to the resource, and we will grant it only if that particular request edge will not form a cycle upon converting that to an assignment edge. in this case, we can easily find out that it is an unsafe, because when we are changing that back to the assignment, when it makes a request, again we are making an assignment, you can see very well this particular resource allocation graph is forming a cycle, that is, it's unsafe. The previous resource allocation graph is suitable only if there is a single instance of each resource type. In case if there are multiple instances of resource type, we have to use the banker's algorithm to avoid the deadlock. Here, each process must declare the maximum number of instances of each resource type that it may need, the priority information. When a process is requesting a set of resources, system must determine whether the allocation of these resources will leave the system in a safe state. If the system is safe, resources are allocated. Otherwise, it has to wait. When a process gets all its resources, it must return them in a finite amount of time. These are all the data structures used for the banker's algorithm. N represents the number of processes. M represents the number of resource types. Available is representing how many instances of the resource types are available. That is, available of J is equal to K, which means K instances of the resource type Rj is available. Max is an n cross m matrix. If max of I comma j equal to k, which means Pi is a process may request at most k instances of the resource type Rj. Allocation is an n cross m matrix. Allocation of I comma j equal to k, that is, process Pi is currently allocated with k instances of the resource type Rj. Need is an n cross m matrix, that is, if need of I comma j equal to k, which means process Pi may need k more instances of resource Rj to complete the task. So if we want to know what is the need matrix for a particular process, we can subtract the current allocation from the maximum. We will be able to find out the need matrix. Safety algorithm. This algorithm is used to check whether the system is safe or not. Step 1. Let work and finish be the vectors of length m and n respectively. We need to initialize the work as available and finish of I is false for all the values of I, 0 to n minus 1. Step 2. We need to find a process I such that finish of I should be false to that particular process. Also, need of that process should be less than or equal to the work, which means the availability. Once we are able to find out that particular process, we will allow that process to complete the task by allocating the resources, and after the completion of the task, the process will return the allocated resources. So the work becomes work plus allocation, and that finish of I is equal to true. We are setting the finish status true. Once that process completes, we are moving on to the next. Go to step 2 to find the next I value. So we are repeating it. At a particular point of time when we are not able to find such a I value, we'll go to step 4. So in the step 4, we make a check whether finish of I is equal to true for all I, then the system is in a safe state. This is how the safety algorithm is going to work. The next is the resource request algorithm for process PA. So the banker's algorithm includes safety algorithm, which is used to check whether the system is safe or not, whereas this resource request algorithm is used to decide whether to grant the request. When a process makes a request, whether to grant it or not. Initially, the request will be equal to the request vector for that process PI. So request I is equal to the request vector. If the request vector is equal to k, it's understood that the process PI wants k instances of that particular resource type Rj. The first step is we need to check whether the request made is less than or equal to the need. If that is the case, we'll proceed. Otherwise, we'll raise a error condition because a process has exceeded its maximum claim. It needs some resource, but it is making a request more than that. So we have to raise a error condition. In case if this condition is true, we'll go to step 2. In step 2, let us once again check whether the request is less than or equal to the availability. If the request is less than or equal to the availability, we can proceed to step 3. Because if it is more than the availability, we can't provide those resources to the process. So we are checking this condition. If this is not true, the PI has to wait. Since the resources are not available, it is making a request more than the availability. In case the request is less than or equal to the availability, we will go to step 3. So here in step 3, we pretend to allocate the requested resources to PI. That is, we are allocating the resources to the process. Once we are done with the allocation, the available gets reduced. So available equal to available minus request. So from the available, we are providing the request. We are taking the resources and we are providing it to the process. So your available becomes available minus request. Also, the process has some allocation to it. So allocation to that particular process PI will be equal to the old allocation as well as the new allocation. So allocation becomes allocation plus request. And need. Need is equal to need minus request. So it has made a request, we have provided it. So need becomes need minus request. If this is safe, then the resources are allocated to PI. So we are pretending that we are doing the allocation and we are checking whether the system is safe or not using the safety algorithm. If it is safe, we are providing the resources to the process PI. In case if it is unsafe, the process has to wait and the old resource allocation state is restored. This is how the resource request algorithm is working. Thank you.